In this video, we're going to look at an example problem for impulse and momentum. So this is just an example. In this question, we're going to solve the case where we have here a package or a bag or something, and it's landing on a cart. And the cart was initially stationary, so V naught of the cart is equal to 0. The speed of the bag is equal to 3 meters per second. The mass of the bag is 10 kilograms. Mass of the cart is equal to 25 kilograms. And there's no friction along surface, so cart rolls freely. And the question is asking us to find the final velocity of the cart. So the velocity of the cart after the package has hit it. It's asking us to find the impulse exerted by the cart on the package. So impulse exerted by the cart onto package. And the question is also asking us to find the fraction of initial energy lost in impact. So this question has two particles with impulse and momentum. And in this case, we're going to have, in some direction, some conservation of momentum, but we need to figure out where that would be. So in order to do that, we actually have to draw 9 different diagrams, which is going to seem like a lot, but it really helps you visualize what's happening. So I'm going to start off by drawing the impulse momentum diagram of just the bag. So here we have the bag, and it's coming in MB, VB, and the angle is 30 degrees. So we could even draw it this way as well as 30 degrees. The reaction force on that bag, we don't know what it's going to be, but because it's coming in at an angle, we know there's going to be a reaction force in the x direction. This will be our I of x. And we're also going to have a reaction force in the y direction, in IY. Once the bag hits the cart and starts rolling, it's then going to be moving only in the x direction because the cart can only slide in one direction. So MV2 is going to be moving to the right. So you can see here that a cart originally has, x and y components of a velocity. There's reaction forces here, and then in the end there's only a velocity going to the right. Now we'll look at what's happening for just the cart. So now what you do, I'm going to move the screen up. So now we have just the cart here, and there's no velocity, so you can just say m cart, velocity cart is equal to 0. Now the reaction forces here on the cart, first we need to have an equal and opposite reaction to these impulse forces, because this cart here at this moment, the parcel here, the bag is hitting the cart here, so these reaction forces have to be equal and opposite on the cart. So here we have an IX and an IY. In this case, these are the forces between the bag and the cart, but the cart is also on the ground, so there's going to be another reaction between the cart and the ground. So I'll just call this here, I'm going to call this impulse to Y. I should have done that in red here. And this is going to be equal to, the cart is going to then have a velocity here, mv2. And I'll just label this bag and cart. When you look at this drawing, it makes sense that you would need to have an impulse here opposing this impulse here, right? So here you have forces down from the bag onto the cart, and then the ground reacts, in this case equal and opposite upwards, because we only have motion going to the right. If these forces here didn't cancel out, that means that we would have movement here in this direction, right? So now we draw another set of 3 that combines the 2. So I'm going to scroll up. Actually, I don't have to scroll up. So then here we have the cart and the package. Here, this is the MBVB and the MCVC equals 0 plus. And now for this one, we only draw the external forces. So here we would have the cart landing on the package hitting on the cart. And now when we combine these, this force here cancels with this one. This force here, I of x, cancels with this one. So all we have left is this impulse here. So this is impulse 2y. And this is all equal to the motion of the cart and the bag combined moving to the right. Now here you have m bag plus m cart times v2, because they'll then be going in the same speed. So you have to make sure that your diagrams tell the entire story of the motion. Now, in this first row here, do we have conservation of momentum? Remember, conservation of momentum, the formula for that was, if you have conservation of conservation of momentum, it means that your summation of mv1 is equal to the summation of mv2. So in this first row, is that true? Oh, and I should draw my vectors here. The answer is no, it's not true, because here, the momentum here is not equal to the momentum here. You can see very clearly they're going in different directions, right? So momentum is not conserved in this row. Is momentum conserved in this row, in the second row? It's also not conserved. Here we had no momentum, and here we have momentum, so not conserved. But in this bottom row, is momentum conserved? In the bottom row here, we only have a force moving upwards. So momentum is conserved in the x direction. There's no force in this drawing in the x direction, which means whatever component of momentum was going in the x direction here, that's equal to the linear momentum in the x direction here. And you know that because here there's no forces in the x direction. So I know this is a lot of drawings to draw out, but here it becomes very clear to see where your momentum is conserved. So now, to answer number 1, the final velocity of cart, we use our conservation of momentum in the x direction in our row 3. So I'm going to move this up. I'll just have row 3 showing. So here, to solve the first part, we look at this system. So we're looking at both particles in the x direction. And we have MB times velocity of B cos 30, so just the x component, plus 0, because the velocity from the cart is 0, is equal to the mass of the cart plus the mass of the bag times V2. In this case, we know this, we know this. The masses aren't changing. We can solve for V2. We get V2 is equal to 0.74 meters per second to the right. That's the speed of both the cart and the package, the parcel. The next question is asking us to find the impulse exerted by the cart on the package. So I'm going to show the pictures again. So which row should we use to solve this question? So for this one, we're actually going to use row number 1 here, because the impulse of the cart onto the bag is going to be the resultant of this and this combined. If we use the second row here, this impulse 2 between the wheels and the ground is going to get in our way. So we want to use this row here to solve for the impulse exerted by the cart on the package. So I'm going to scroll up again, and what this looks like is B. Here we have the mass of the bag times the velocity of the bag cos 30, so in the x direction, minus the impulse from the cart in the x direction is equal to the mass of the bag times that second velocity. We solved for this velocity up here, so we have it. We know our masses, and we know our initial speed, so we can solve for our ix. In the y direction, we have the same thing. This time, I'll just scroll down for a second. This time, our velocity initial was sort of coming down in the y direction. In fact, I forgot to draw this. So here we're using positive directions like this. So here we'll have the mass of B times velocity of B in the y direction, so it'll be minus, plus this impulse here from the cart is equal to 0 because there's no velocity here in the y direction. So if I scroll up, we would have MB VB sine 30 plus IY, sorry, this is minus, equals 0. Solving these equations, you get I of x is equal to 18.56 newton seconds to the left, and I of y is equal to 15 newton seconds upwards. I'm going to run out of time, and I want to get through this question in this video. So the total impulse here would be the resultant of these two. The magnitude would be the resultant. Here I'm just going to leave it in component form. Now, for the fraction of energy lost in the impact, here we can look at the energy before and after. So the total energy of your system in the first state was all driven from your bag. So it was your kinetic energy would be 1/2 mv squared. In this case, there's only velocity of the bag. So here you would have 1/2 times 10 kilograms times 3 squared, which is equal to 45 joules. Afterwards, now we have motion of the bag and the cart, so we would have 1/2 times m bag plus m cart v squared. So now we have 1/2 times 10 plus 25 times 0.74 squared, and this is equal to 9.58 joules. So the energy lost during the impact is 45 joules minus 9.85 joules, which is equal to 35.4 joules of energy lost. So in this case, even though we had some conservation of momentum, we did have a loss of energy here in our system. So conservation of momentum does not guarantee conservation of energy.